Hello everyone, I'm Michael Frank and welcome to day 2 of the Reversible Computing Workshop, and today's topic is device and circuit technologies for reversible computing. If you haven't seen the schedule, today is similar to the other days of technical sessions. We have plenaries in the morning, panel, lunch break, and then a break session in the afternoon, and these are Pacific time. Just as a brief outline for today, I'll start with a little bit of motivation and history. We'll then talk about the two major approaches to physical implementation of reversible computing, which are the adiabatic approach and the ballistic approach. And then looking ahead, I'll say a little bit about what is needed in terms of new technologies and what are some key figures of merit and requirements that a new reversible technology needs to meet. So first, a few words on motivation. I already showed this slide yesterday, so just to recap briefly, conventional computing based on non-reversible digital logic is reaching some pretty fundamental thermal limits in the near future, and those will impair our ability to continue improving the overall cost efficiency of computing, since energy is a component of cost, unless we start doing things differently. And I argue that we can basically infer from fundamental physics that if we want to do general digital computing, we essentially have to start using the reversible computing paradigm. It's the only physically possible way to continue scaling, in principle, indefinitely. We don't know any fixed limits on that. And so this could have major economic impacts in the long term, especially insofar as the economy comes to rely more on computing, more and more becomes a larger share of economic activity. So I already talked about the reasons why reversible computing is the way out of this dilemma yesterday, and it comes down to Landauer's principle. And so I won't talk about that again, but I want to mention, in Landauer's original paper, he did start hinting at physical implementation techniques such as this bistable potential well paradigm. If you store a bit in the state of a system that's some minimum energy state and they're separated by a potential barrier, there are ways to manipulate this potential energy surface in such a way as to do computation. And Likarev described this in somewhat more detail in a context of superconducting circuits in the 70s. Charlie Bennett also talked about stochastic realizations of thermodynamically reversible computing using biomolecules or a mechanical clockwork apparatus. And Fredkin and Toffoli talked about ballistic models of reversible computing, such as their conceptual billiard ball model, which has some practical difficulties, but today we're working on new circuit techniques that can realize this type of ballistic model without some of the problems that the original billiard ball model had. So a lot of the early concepts that were explored in the 60s through 80s still apply today in the present technologies. So first, we'll talk in a little more detail now about the adiabatic approaches and what they involve. First, some general requirements for a process to be highly adiabatic, or in other words, to not involve much entropy increase. If you're performing some transformation of a system, you want to be careful not to transform it so quickly that you end up exciting undesired oscillatory modes or higher energy states of the system, because then those can decay, causing dissipation. and they represent departure of the energy of the system from its desired trajectory. So because of that, the process should happen slower than the natural relaxation timescale of the system, but it also should not happen too slowly, because there's also generally equilibration processes that can occur where the active energy in the system leaks out to the environment and becomes dissipated as heat, and so you want the transition to happen quickly compared to that time scale. And so in order to meet both of these constraints and stay well away from the time scales that you want to avoid here, we essentially have to move apart those time scales. So we want to decrease the relaxation time scale as we refine the technology and increase the equilibration time scale. And it's easy to give examples of what this means in classic cases like adiabatic compression of an ideal gas, where you don't want to excite pressure waves in the gas, but you also don't want the heat of the compressed gas to leak out. And there are analogous things in the electrical domain, like if you try changing things too quickly, then you get you can excite the inductive degrees of freedom of the system, and if you do things too slowly, energy can leak out of your circuit nodes through various mechanisms. So just a brief review of the history of adiabatic circuits in CMOS. This started with Fredkin and Toffoli, who had an early DARPA proposal where they discussed concepts for implementing logic with switching circuits with capacitors and inductors. This wasn't very well fleshed out, and so there were additional developments over the next excuse me, roughly the next 15 years, until Syed Yunus and Tom Knight in 1993 described their charge recovery logic circuit technique, which was the first fully adiabatic approach to general sequential digital logic, including pipelining. And you know, this is something it's not so obvious how to do it at first, and so this was a nice innovation, and this has been improved upon over subsequent years at a gradual pace. The first improvement was by Yunus and Knight themselves, who the next year came up with a somewhat simplified version of CRL called SCRL, and then in the subsequent project at MIT, which I was a student on, we designed several processors at varying degrees of complexity, just to show that there was nothing inherently impossible about doing computer architecture in this fully adiabatic and reversible style. There's been a bunch of other literature on adiabatic circuits more recently, but unfortunately most of it is are designs that are not actually fully adiabatic, and so they don't actually they can't approach the ideal of reversible computing. Whereas at least in the limit of low leakage, CRL and SCRL could in theory do that, and we've also been playing with some circuit techniques at Sandia more recently that try to do that. Okay, so just briefly a few words about adiabatic switching and CMOS. The way we do this is that instead of having a constant supply, we have a variable voltage supply that ramps up over some period of time. And through standard analyses, one can show that the energy dissipation in that transistor has this form where it scales down as the time for the transition increases. So this gives you a trade-off between the performance per unit hardware and the energy efficiency, which translates to performance per unit power dissipation. And you find that as hardware gets cheaper, it's advantageous to start trading off more hardware to gain energy efficiency. And we'll talk more about scaling tomorrow, um, but the upshot is that these approaches will become increasingly favored economically as transistors continue to get cheaper, but the energy efficiency of conventional approaches stops improving. Just one brief note here, although it's not obvious, the theory of why the circuit approaches adiabatic operation in the low speed limit is actually tied to the fundamental Landauer's principle and to reversible computing theory, but to see that as non-obvious, the traditional model of reversible computing is kind of adequate to understand that connection. And so there's a link to a paper here that explains that in much more detail, but I'm not going to go into that today. So recently in the last few years at Sandia, we've had a project to essentially do some demonstrations of reversible computing in CMOS, and the rules for designing fully adiabatic circuits in CMOS have been known for some time, but there haven't been a lot of physical chips made to demonstrate how energy efficient adiabatic circuits can be if you follow all the rules correctly. And so that's what we're trying to do. This is the initial circuit we worked on, which is it's a simple shift register that actually, the roots of this go all the way back to the original CRL technique. It's a little simplified compared to the CRL shift register, but it's essentially the same concept. And in our simulations, we found that in the 180 nanometer process at Sandia, that we should be able to run this circuit with a dissipation of a few attojoules per transistor per clock cycle, and that's only tens of electron volts. And this is quite a lot smaller than energy dissipation for even end of roadmap CMOS, so that's a nice result. To validate that experimentally, we taped out a test chip just this last August, and when we get those back, we're going to do some experimental validation and verify this prediction empirically, or try to verify it. One limitation of this circuit style is it's a dynamic logic, so some of the circuit nodes are floating, not connected to any supplies for part of the clock cycle, and that leads to some potential problems with voltage level drift and sag, and can lead to additional dissipation. And since we're really trying to aggressively minimize dissipation, we just recently invented this newer circuit style, which I call S2LAL for static two-level adiabatic logic. And the clock period here is twice as long as 2LAL, and you need twice as many clocks. But it has the advantage that it's fully static, and I believe that this logic style will prove to be more energy efficient than any other semiconductor-based logic family known today, although we've got a lot of work still to do to prove that. One thing that might be necessary for realizing that prediction is aggressively minimizing leakage power through reduction of subthreshold currents by operating at low temperature, and optimizing the device structure to also reduce gate leakage currents. So anyway, that's enough about that for now. Now I'll take a few minutes to talk about some of the ballistic approaches we've been exploring. And as I've said, these trace back historically to the Fredkin and Toffoli billiard ball model, which is pictured here. And there's a small subfield called collision-based computing that is using that as the inspiration for computational techniques based on propagation of pulses in various media. And one of the nice things about this uh, approach is that you don't need an explicit clock, that um, operations happen when the data arrives, and you also don't need an explicit power supply at the logic gate level. Just the energy to perform the operation is carried by the data signals themselves. Of course, the problem with the original billiard ball model and with a lot of uh, realizations of it is that there's this implicit, precise synchronization between the arrival times of these incoming balls, and it's not a good assumption. And in fact, what you will find in practice, if you tried to, to build this structure in reality, is that you'd have sort of chaotic amplification of errors in time and position of the balls, and this would cause the system to quickly become unstable. Um, so one thing that I was trying to do for a long time and recently figured out how to do in late 2016 was to come up with an asynchronous ballistic style of reversible computing. So instead of having the inputs being synchronized, we explicitly require them to come in at different times. And this has the nice advantage that now the behavior of the device is independent of the precise time difference between the arrivals. So, uh, so basically, it should be much more stable. Um, we figured out how to do universal computing with devices in this family, and we we started an effort to implement this in superconducting circuits. This is the simplest possible circuit in this family of asynchronous ballistic reversible circuits, and it's what I call a reversible memory cell. So if we have an incoming flux soliton that holds a quantum of magnetic flux, it's going to essentially exchange polarity with this stored fluxon. And that's a reversible operation logically and should be relatively efficient physically. Um, so then we actually figured out how to design this, and I owe some credit to Eric de Benedictis, who suggested I try this very simple circuit topology, and then I played around with parameter values a little bit and got it to work. So this has the desired function in simulation. It's relatively efficient, and so we decided to go ahead and build this. So we designed a test circuit. We did a layout, and then we had it fabricated with some support from the ACI program. And so this is a test structure that allows us to load fluxons into the storage loop, flush them out later irreversibly, and just test the functionality of this circuit. So I've only got a couple minutes left, I think, 1 minute. So just very quickly, looking ahead, what's needed, I mentioned yesterday the fundamental physics work that's needed. But at the device level, we also need to design new devices that have good characteristics, such as low dissipation as a function of parameters such as the speed, the temperature, the size, the mass. We also want to know the energy invested in the operation. And if it's reversible, most of that energy should be recovered and reused. And then cost is an important consideration. Any reversible technology needs to obey certain requirements. It has to have all the properties that you need for any digital logic hardware technique, such as ability to control timing in some way, or in a synchronous style that is relatively insensitive to timing. We want to be able to compose operations, to parallelize operations, to restore signal levels, to have digital stability of signals and reliability and so forth. One important requirement that is often ignored is that the description of the system needs to be self-contained. In other words, it is cheating if you invoke any kind of external control and then don't analyze the driving system as well and the interaction between them. So for example, in adiabatic CMOS, if you're not careful with how you drive those transitions, you may not save any energy at all. You're just sweeping it under the rug, and it all happens in the external driving system. And although I didn't talk about it today, part of the work that we do here at Sandia is on designing resonant oscillators to drive our system in an efficient energy recovering way. We have to support either adiabatic or ballistic operation, or perhaps some novel approach that is neither of those, but I think most realistic approaches will include both of these aspects to some degree. You know, it needs to be capable of performing universal logic, and to be able to do that in a way that is close to thermodynamically optimal, both for reversible operations as well as for irreversible operations, which may actually be desirable in optimal algorithms. So some optional features are the ability to do stochastic operations, although it's not clear that that actually helps algorithmic asymptotic complexity for any problems. And then of course it would be really nice if we could also do quantum computing in the same technology, but I think that's a very long-term goal. So anyway, about it. This is a conclusion slide, which I won't read, but sums up what I said. And the rest of the talks in this session will go into more detail on specific techniques. And also some of the talks in tomorrow's session also address device and circuit level issues. So you should look at tomorrow's program as well if you're interested in this topic. And that is it. Thank you very much.